We're going to take a little break from quadratics for the next couple sections, and we're going to get into some exponential functions. And we all know what exponents are. It's raising something to some power. Okay, but exponential functions, well, let's talk about where they come from. So the first, we've dealt with linear functions, right? And that was our y equals mx plus b. And it made a line, right? Linear. And if you notice, all we're doing with our x term is just being multiplied by some number, some constant number. So it increases at a constant rate. And then we dealt with quadratic functions. And our standard form here was ax squared plus bx plus c, y equals. And if you notice with our x term, we're squaring the x term. We're squaring the x term. And so it ends up making, kind of goes down, comes back up, it's symmetrical. So we call it a quadratic. So lastly, an exponential, which we have up top here. What we do with our x term is we actually raise some number by our x term. So as we move in the x direction, increase by 1 each time, it's going to exponentially it's going to grow fast. And so it'll look like something like this. It looks something like that. And I like to, when you hear the word exponential, I hear it a lot in sports. If I'm watching ESPN, for example, the Bulls right now, they're missing their MVP player, Derrick Rose. Well, he's going to come back very soon. And so a broadcaster might say the Bulls will exponentially get better when Derrick Rose returns. And what they mean is right now they're just kind of on their pace. Once Derrick Rose returns, boom, they're going to get better in a hurry. They'll get better in a hurry. That's what exponential means. It's going to go up fast. Okay? So let's take a look at our standard form of this exponential stuff here. So y equals ab to the x power. Just raising the b to the x power. Okay? A can't be 0 because then it makes the whole thing 0. B has to be greater than 1. If I would have b to be a negative number, when I would make a table for this, at every odd I would have, I'd have a negative answer for my y, right? Because I'm going to take a negative to an odd exponent. It's multiplying an odd number of negatives. And every even I'd have as a positive. So my graph would look pretty funky, right? So I do not want to use a negative for the b term. And lastly, b cannot be 1. If b was 1, 1 to any power, 1 to the first power, 1 to the second power, 1 to the third power, they're all just 1. So I'd end up with a straight line. And we're not worrying about straight lines. So different examples, I could have it where there's no a term. I could have something just like 3 to the x power. I could have it with a fraction, 1/3 to the x power. And then I could also put a coefficient on it and say something like 2 times 4 to the x power. Okay, lots of different ways we can see it. Let's just take a look at what it looks like here. Here I have y equals 3 to the x power graph. Y equals 3 to the x power. Well, we don't have any special rules on how to graph these, so if we don't have special rules, we just make a table. And every time we make a table for this, when we graph, I'm always going to pick these x values. -2, -1, 0, 1, and 2. I want to get a couple negatives, a couple positives, and then see what happens when x is 0. Okay, so we'll be making a table for every single one of these exponential functions. So we're just going to quick look at this one. Let's look at when we plug in 0 for x here. When we plug in 0 for x, that's just y equals 3 to the 0 power. Well, anything to the 0 power is 1. Anything to the 0 power is 1. That's a review from last year. Anything to the 0 power is 1. So that's graph there, 0, 1. Then when you plug in 1 and 2, anytime you plug in a positive number, it's going to grow fast, right? It's going to grow fast. 3 to the first power is 3. 3 to the second power is 9. If I did 3 to the third power, if I plugged in a 3, I'd get 27. Boy, that would be way up there, right? I wouldn't be able to even reach that on this graph that I have here. So it's going to increase fast. Well, as I go in the negative direction, if I plug in a -1 and a -2, it actually ends up decreasing. Because if I look, 3 to the negative first power, if we remember the rule, is really 1 over 3 to the first, so 1/3. 3 to the negative 2 power is 1 over 3 to the positive second power, which is 1 over 9. So it's decreasing. It's getting closer to 0. It's never going to get to 0, and it's never going to go negative. So you notice how your graph just kind of bottoms out by the x-axis there. It never goes below it. That's because it won't ever become negative. As I get to a bigger negative x value that I plug in, it's just going to be a smaller and smaller fraction. It's going to get closer and closer to 0. Okay, let's do another example to get a look at this. So it tells you to graph the function, find the y-intercept, and state the domain and range. Okay, I didn't do that in the last one, but we'll do it here. Then use the graph to determine the approximate value of the given expression to the nearest 10. So what we're going to do is we're going to graph our y equals abx, ab to the x. So y equals 2 times 8 to the x. And then we're going to plug in negative 0.5 for x. And we're going to look at our graph and make an estimate of that. And we'll go through that here. So first things first, let's make our table. X, y, and just like I said, we're going to pick negative 2, negative 1, 0, 1, and 2 for everything. So we get some negatives, get some positives. And I'm going to plug in the 0 right away because that's the easiest one for me to do when x is 0. So I got y equals 2 times 8 to the 0. Well, anything to the 0 power is 1, and 2 times 1 is 2. So I plug in a 2. I'm going to go ahead and graph that. 0, 2. Then I go ahead and I do when x is 1. I'll do my positives next. So y equals 2 times 8 to the first power, which I get 16. So I got 16 here. Oh, that's going to be way up here. And I plug in a 2. And I get y equals 2 times 8 to the second. This is going to be a big number, isn't it? 2 times 64, 128. Holy buckets, okay? So I know this is things going way up fast. I can't even graph that. I might have to change my scale here. I still wouldn't even be able to get it if I changed my, this would be, so we're going to leave this like this. I'm going to just count by ones. So I got 128. Now let's go ahead and I'll plug in my negatives. So I'm going to plug in when x is negative 1. So I got y equals 2 times 8 to the negative first power, which is 2 times, that's 1 over 8 to the first, right? So it's really 2/8, which is 1/4. So I got 1/4 there. Remember, you won't get a negative answer. It's just going to be a fraction every time. Same thing, let's plug in when x is negative 2 now. So y equals 2 times 8 to the negative 2 power, which is 2 times 1 over 8 to the second, and 8 to the second is 64. So it's really 2 over 64, which is 1 over 32. So if I look, I got negative 1 and 1/4, somewhere in there, and then even smaller. It's going to be very hard to graph, right? Negative 2. I know it's going to get closer to 0. So when I graph this, it's going to go on forever in the negative direction, but it won't cross or won't touch the x-axis there. And it's going to go up and up and up and up and up. And it's going to keep going. It's going to increase. Okay? So let's take a look at this. My y-intercept, here's my questions now. My y-intercept equals, well, 2, right? Where it crosses the y-axis. So y-intercept is 2. The domain are my x's. Well, it's going to go on forever in the negative. It's going to go on forever in the positive, right? I can plug anything in for x in my equation, and I'll get an output. So the domain is all real numbers still. All real numbers. And my range now, remember, it never crosses the x-axis, right? So it's never going to go to 0 or below 0. So it's never going to go to 0 or below 0. So I won't put less than or equal to. Okay, and it goes on forever in the vertical direction. So my y has to be greater than 0. And I can flip those around. Doesn't really matter. Y has to be greater than 0. And that's going to be for every single case, right? Because it can't be 0. Right? It'll never touch there, and it'll go on forever in the vertical direction, going up. So y is greater than 0. Okay, so just make your table. Same thing, even if I have a fraction in there, 1/6 to the x power. I make a table. An xy table, pick -2, -1, 0, 1, and 2. All right, I plug in when x is 0. So y equals 3 times, well, anything to the 0 power is just 1. I'm going to simplify this pretty quick. It's really 1/6 to the 0 power, right? But that's just 1. And 3 times 1 is 3. So I got 0, 3. Go ahead and graph that. And then when x is 1, I get y equals 3 times 1/6 to the first power. So it's just 3 times 1/6, which is 3/6, which is 1/2. So I got 1 and 1/2 to graph there, 1 1/2. Okay, and then when x is 2, I plug into the second power. So I got y equals 3 times 1/6 to the second power, which is 1 over 36. So 3 over 36, which simplifies into 1/12. Okay, so it's working its way down to 0, but it'll never actually cross 0, right? And then I got to plug in all my negatives, -2 and -1. So when x is -1, I would get y equals 3 times 1/6 to the negative first. Well, remember, it just flips my fraction here. So 3 times 6, actually. So we get 18. To the negative first, if I want it to the positive first, it just flips my fraction. So 18. And then when x is -2, that's really 3 times 1/6 to the -2. So it's really 3 times 6 to the positive second power, right? Flips it, and it makes it positive, so y equals 3 times 36, which gives us 108. So it's going to go up quick again. It's going to be like way up here. So here's my graph. Oh, it's going to go up quick again. If you notice, the graph got kind of flipped around the y-axis. So if I have a fraction that I'm taking to the x power, it kind of flips how my graph works, right? Flips it around a little bit. Okay? And my y-intercept, just look at my graph, it's 3, right? We're across the y-axis. Domain, same thing, all real numbers. It's going to go, I can put in any x. And range, same type of thing. Y has to be greater than 0. So that's going to be the same all the time. It's going to be the same all the time. So one thing we notice with our graphs here, if my b, last thing, we can determine whether our data is going to have exponential behavior or not. So basically, as I go in the x direction, is it going to keep getting multiplied up and up and up? So let's take a look at this. It looks like my x's are increasing the same in both problems. So I got a constant rate of change there, I got a constant rate of change here. That's good. So let's take a look at our y's now. Let's take a look at our y's. Well, these aren't going up by the same amount, are they? But over in number 2, it looks like they are. Plus 5, plus 5, plus 5. So over here, this is a constant rate of change, right? As I go up 3 in the x direction, I go up 5 in the y direction. So I kind of get a linear look. It's a constant rate of change. So this one does not have exponential behavior, right? Because it's going up by the same amount each time. To check for exponential behavior, we want to see if it's being multiplied by some number each time. We want to see if it's being multiplied by some number. To check that, I can just divide 2 consecutive y's. So I can take 25 and divide it by 10. And then I can take 62.5 and divide by 25. And 156.25 divided by 62.5. And see what I get for those. And as I go through them, I end up getting 2.5 for each. Every single one is 2.5. So it's basically getting multiplied by 2.5 every time. So this would have exponential behavior because it's kind of like 2.5 to the x power. As my x's go up 1, I keep multiplying by 2.5. Or in this case, as they go up 10, you get multiplied by 2.5. So This one has exponential behavior. So I would say yes, and this is kind of how I explain it, because I'm multiplying by the same number. If it's being added by the same number, it's no, because that's linear. Okay, there might be some questions tomorrow, but that's why we got plenty of time to work. Hope you learned a little bit about exponential behavior. Deuces.